Hello and welcome back to Gen Chem with Dr. J. I'm Dr. Janita Pritchett, and on this channel we talk about all things Gen Chem related. In this video, I'm going to be covering molecular acids, and we're going to learn how to name them. Let's get started. So in the previous video, I briefly introduced this idea of molecular acids. And these are molecular compounds that have this hydrogen ion that is formed whenever they're dissolved in water. And so these are different than other molecular compounds because indeed they do create these electrolyte type solutions. They have these ions that are generated as they dissociate. And so when we're dealing with acids, that the material has been dissolved in water, we typically will write them with the AQ or aqueous designation after the formula. And again, that just simply means that it has been dissolved in water. So what are some common characteristics of acids? Well, think about acids you've encountered before, like citric acid. It tends to be very sour in taste. It has the ability to dissolve many metals through a single displacement or replacement type of reaction. And for the most part, when you encounter them, they're generally going to start with that hydrogen atom in the cation position. So some examples you see here is HCl or H2SO4. So shown here is an example of an acid reacting with a metal. And so in this case, we have hydrogen gas that's being produced as we react our hydrochloric acid, so HCl, plus zinc metal. And so if we recall back to a previous video where we learned about different types of chemical reactions that occur, this looks like a single replacement reaction. And so we can actually predict what we would see if this reaction were to occur. Since zinc is a metal, it would swap places with the cation, and the resulting equation would end up giving us zinc chloride plus H2 gas being kicked out and released. And remember, we're writing H2 because hydrogen is a diatomic element. And we would just simply need to balance that out. But as we actually dissolve these metals, we would see this hydrogen being released, that's something new being formed, and as a result, we would likely see a lot of bubbling occurring when this reaction takes place. So there are two main categories of acids that we're going to be dealing with, and we're going to learn how to name these two, okay? So again, the overarching idea is that acids are going to be a chemical that has H as the first element. And then we can break this into two subcategories. There are binary acids, and if we break that word down, binary means two. So a binary acid has hydrogen as the cation and something else as the non-metal anion. So two elements are present. And an oxyacid, if we break that word down, oxy means there's some oxygen present, and that's the result of having a polyatomic ion combined with the hydrogen in this molecular formula. So again, there's two different naming systems that we want to be aware of, one for binary acids and one for oxyacids. So when you're dealing with naming a binary acid, we're going to be using the hydro prefix, as shown here. Then you're going to take the base of the nonmetal, drop the ending, and add ic. And then we add the word acid at the end. So for instance, if we had something like HCl, we see two letters. So we would say hydro. Chlor is the base of the nonmetal. Ic, add that ending, acid to complete it, okay? And so again, hydro prefix, follow with the nonmetal name, and then add that ic ending. All right, and so again, here you can see this example with HCl that I've already walked through, and we know that there's the chlorine ion that's present. We know that that would make it chloric, and hydrochloric would be the prefix added, and then we add acid to the end. All right, now when we're naming oxyacids, we no longer use that hydro prefix, okay? We no longer use that hydro prefix. Now what we're going to be doing is taking the base of the polyatomic ion, and then if that polyatomic ion ends in ate, it gets the ending of ic, okay? So for instance, chlorate would become chloric. And if the polyatomic ion ends in ite, then the ending becomes us. So if it was chlorite, that would become chlorus. and then we add the word acid at the end. And this naming system really helps us to distinguish these things. So if we had something like HCl, which is a binary acid, versus HClO versus HClO2 versus HClO3 versus HClO4. Well, now by incorporating these two naming systems, we can name each of these differently. So like HCl would end up being hydrochloric acid. Again, we're using that prefix because it's a binary acid. This here is hypochlorite. So ending, the us ending would become hypo, which is different than hydro. That's part of the name, hypochlorous acid. The third one, that's chlorite. So that would become just chlorous acid. HClO3, well, ClO3 is chlorate. So this would become chloric acid. And then ClO4 would become perchloric acid. Okay, so when you're doing this naming, you got to first figure out, is it a binary acid or oxyacid, and apply the appropriate prefix if necessary and or ending. So let's try naming this one. We have H2SO4. And so we can see this is an oxyacid because I see more than two letters. It's not binary. There's a polyatomic ion, which is sulfate. So if it's sulfate, then we're going to drop that ending and turn it to sulfuric. Okay. And then we add the acid to make it the complete name. So sulfuric acid. Whereas something like H2SO3, again, oxyacid, we see that we have sulfite present. Ite will turn to us, and so that becomes sulphurous acid once we add on that ending. So let's try a few examples. We have H2S, so two letters means it's binary. So we will use the prefix, so this will be hydro. Then we have sulfur, so we're going to add the ending sulfuric acid, which is different than sulfuric acid, which would be H2SO4. HClO3 we already did, but we can do it one more time. We see that we have a oxy acid, we have chlorate present, no prefix is used, so it would become chlorate, ate becomes ic, so chloric acid. And then HNO2, well, oxyacid, I see nitrite is present, so ite becomes us. So this will become nitrous acid. Now, similarly, if we can get the name from the formula, we can also get the formula from the name. And so when we're writing the formula for an acid or predicting the formula for an acid, remember it's going to start with a hydrogen, H. And we're going to treat it like it's ionic. And so we're going to be assigning charges and crisscrossing down, remembering that that hydrogen takes on a +1 charge. If you don't remember your polyatomic ions, head back to chapter 3, where I discuss polyatomic ions and how to incorporate them into naming. So the hydro prefix, if you see that written, again, that tells us it's two letters or two elements that are present, binary acid. And so we would have the two letters, two symbols, assign the charges, crisscross down. If there's no prefix, then it means it's an oxyacid. And remember, if you see ic, that means that the ending is ate. And if you see us, that means the ending is ite, okay? All right, so if we have hydrosulfuric acid as a binary acid, when we're trying to come up with a formula for that, well, we know that hydro means that there's two, it's a binary, two symbols present. So hydrogen, sulfuric would be sulfur. Then now we're going to be assigning charges. So hydrogen is that positive charge. Sulfur is 2-, group 6. We crisscross down. So bring it here, and we end up with H2S as our hydrosulfuric acid formula. What about carbonic acid? Carbonic, when I see that, I don't see hydro, so that automatically tells me there's a polyatomic ion present. Because it's an acid, I know it starts with a hydrogen. And then carbonic would mean it's carbonate, which is CO3. and that has a 2 negative charge. Remember, your hydrogen is a positive charge. We've assigned the charges. We're going to crisscross down. So bring it here, and we end up with H2CO3. And again, we would add that aqueous designation to signify that it's dissolved in water. What about sulfurous acid? So sulfurous means there's no, it's not binary, there's no prefix. Us means that it ends in ite. So sulfurous would be sulfite. That would be SO3 with a 2- charge. We know hydrogen's involved because it's an acid. Add the charge, and we crisscross down, and we end up with H2SO3. So let's try predicting the formulas for the following acids. Chlorous acid, us, no hydro prefix, tells us that we have a polyatomic ion. Us means it ends in ite. So chlorous would be chlorite. Chlorite is ClO2. It's an acid, so there's hydrogen present. +1, -1. No subscripts are needed because when we cross that down, they would just simply cancel out. All right, phosphoric acid. Again, no hydro present, so that means there's a polyatomic ion. Phosphoric means that phosphate 8 is present, so PO4 with a 3 negative charge. Hydrogen, again, because it's an acid, positive charge, crisscross, and we end up with H3PO4. And then last but not least, hydrobromic acid. The hydro prefix tells us that it's binary, so 2 letters are here. So what letters? So we have hydrogen. Bromic would be bromine, and so Br. We have a positive charge and a negative charge. Crisscross. Again, those charges we're just getting from the group numbers and the number of valence electrons that it has. Again, if you don't recall how to do that, go back to chapter 2 videos. And here we go. HBr would be our hydrobromic acid. When we think about acids, remember we said that these acids, although they're molecular compounds, they do behave similar to ionic compounds when they're placed in water. They have the ability to dissociate or ionize or break apart to have these charged particles that will then float around in the solution. And that's really because of that hydrogen ion that's present that is able to undergo this ionization process. Now, not all acids will ionize 100%, meaning for every molecule that I put in, I'm going to get these positive and negative completely, it's going to completely dissociate, and I'm going to get nothing but positive and negative ions out. The only ones that are going to completely 100% ionize are things that we call strong acids. So a strong acid, for example, is like hydrochloric acid, HCl. And so whenever you have a strong acid placed in water, it will fully ionize, or about 100% ionize, and you're going to get hydrogen and chlorine coming out. And notice, as we're predicting this dissociation, the relative amount of ions remains consistent with what we started with. HCl has 1 hydrogen, 1 chlorine, and so we see that 1-to-1 ratio still remain. And notice the arrow. Notice the arrow is a complete arrow indicating that I'm going that way to my products and nothing remains. Now, acids that only a small percent ionize, those are considered to be weak acids. And so weak acids, you'll have some ionization occurring, some hydrogen being released, some of the anion being released, but you also will still have some of that molecular compound still remaining intact. And so if you look at the arrow here, if you look at this, sorry, my thing's in the way. If you look at the arrow here, notice how that's that double arrow. And so that's saying that it's indicating to us that some of our reactant remains and we've created some product. Okay, so strong acids, 100% ionize, weak acids, only partially ionize. And so as a result, the strong acids or weak acids are where we're going to get strong and weak electrolytes from. Again, electrolytes, things that create those ions floating around in solution. So strong electrolytes are materials that dissolve completely in ions. So your strong acids or ionic compounds are considered to be strong electrolytes. They will be able to conduct electricity very well. Weak electrolytes are only partially dissolved and only partially ionized. And so they'll conduct electricity, but not as well as our strong electrolytes. And just remember, as you're predicting the dissociation piece, that the polyatomic ion, if it's present in an acid, it's going to remain together as it dissociates. And so you're going to get the hydrogen ion plus the, in this case, acetate ion coming out with the relative amounts remaining the same. So we've hinted to this idea about dissociation and ionization, but we really want to make sure that we are able to predict what would be the dissociation products when you're looking at ionic compounds or these molecular compounds. So when we're looking at ionic compounds in this dissociation process, what we see is in this sodium sulfate. So when we think about dissociation and ionization, this is going to be applied to ionic compounds as well as things like the molecular acids, particularly the strong molecular acids or strong electrolyte type solutions. And so when an ionic compound dissolves in water, again, the ions that are going to be created are based on the ions that are present in the actual compound. And so if we look at sodium sulfide, we see that we have 2 sodium ions that are coming out of the dissociation process and 1 sulfur ion that is being created. And so we actually still in this dissociation process will be dedicating and showing that we have this, two of these ions present. And again, with the polyatomic ions, when we're ionizing something like that, like sodium sulfate, we would create some sodium ions and the sulfate ions, and we adjust the coefficient position to account for how many of each atom or ion is present. And again, with strong acids, when they're dissociating in water, they're going to create ions for the hydrogen as well as whatever anion is present, in this case being the sulfate. And you adjust the coefficient position to ensure that we're maintaining that law of conservation of mass. Okay. And then last but not least, what we're going to do is practice actually ionizing or dissociating these electrolytes that are shown here. And so again, these are all ionic compounds or molecular acids. And so we know we would anticipate that when placed in water, they would ionize. So we want to predict that those ion products. And so if we take calcium chloride, well, we see we would get the calcium cation out, and that has a positive 2 charge. And then we would get the chlorine ion, which has a -1 charge. Notice I didn't put a 2 there. That -1 is based off its group number, its valence electrons. Where I'm going to put the 2 is here in this coefficient position to balance out the number of atoms. And so these would now be all aqueous since they're in water. Okay. Now, if we have HNO3, that's our nitric acid, we would expect it will ionize, and we're going to see our hydrogen ion plus keep that nitrate ion together, which has a -1 charge. And again, we get the aqueous designation because it's now in solution. And then last but not least, ammonium carbonate. Now, ammonium carbonate was one of those situations where we don't have a metal present, but it is an ionic compound because you have the polyatomic ion ammonium present as the cation and then carbonate as the anion. So when this dissociates, I would get my ammonium ion with a positive charge and my carbonate ion with a 2 negative charge. And to balance this out, I need 2 ammonium ions coming out. Again, since this is in water, we could say these are aqueous. I hope this video helped you understand molecular acids, how to name them, and what happens when they're placed in water in this whole dissociation process. Make sure you guys come back to see more videos. Make sure you like, comment, and subscribe, and let me know what additional content you would like to see. Have a great day, and I'll see you guys in future videos. Bye.